Um, Imagine you have a sports car, right?
Hmm.
Like a beautifully engineered, state-of-the-art chassis, but somebody built it completely without a gas tank.
Oh, yeah. Literally impossible to drive.
Right. I mean, without a way to combust the fuel, it's just fundamentally useless as a car.
Mm.
And for decades, making an LED out of an electrical insulator was basically viewed exactly like that, just, an impossible puzzle.
Because you can't plug it in. The material literally refuses to conduct electricity.
Exactly. But scientists at the Cavendish Laboratory over at the University of Cambridge, they just completely bypassed that rule of physics.
Yeah, it's wild. They took a heavy insulator and, through this brilliant manipulation of quantum mechanics, turned it into a working, super efficient LED.
Which is just mind-blowing. So welcome everyone to the Integrate channel. Whether you're, a dedicated subscriber or you just stumbled onto us while looking for the latest tech breakthroughs, we are so thrilled to have you here.
Yeah, thanks for tuning in.
This series is our dedicated space for taking these incredibly dense, kind of paradigm-shifting new findings in the tech world and just breaking them down. And today, we are doing a deep dive into a recent study published in the journal Nature.
And this one, it doesn't just introduce a new device, it honestly rewrites the rulebook for optoelectronics.
It really does.
Yeah.
I mean, the implications of this discovery range from totally reimagining how we do non-invasive cancer diagnostics all the way to, like, how we build the next generation of the global internet.
Yeah, it's a massive leap because, the foundational principle of any electronic device is right there in the name, right? Electronics, you need a flow of electrons.
You need current.
Exactly. In a standard light-emitting diode, an LED, you apply a voltage, electrons move through a semiconductor, and eventually they fall into these lower energy states. We call them holes.
And when they drop in, they release that extra energy as light, as photons.
Yep. But that means the core material has to be conductive enough to let the electrons move, but resistant enough to force that energy drop. That's your classic semiconductor band gap.
Okay, so conductors let everything flow, but insulators, they have this massive band gap, like a literal wall.
A huge wall. It just stops electrons dead in their tracks, which is why trying to build an LED out of an insulator is usually seen as, well, a fool's errand.
Yeah, you apply voltage to an insulator and nothing happens. The charge carriers just sit there.
Right, the energy has literally nowhere to go.
So that brings us to the actual material the Cambridge team was messing with. They're called lanthanide-doped nanoparticles, or LNNPs. And to understand why researchers would even attempt this impossible task with this specific material, we have to talk about why they're so coveted in the first place.
Oh, they are highly prized. The lanthanide series, those are the rare earth metals down at the very bottom of the periodic table. They have a really unique atomic structure.
Their active electrons are deeply buried, right? Like shielded by the outer shells.
Exactly. And because of that shielding, when lanthanides do emit light, it's incredibly stable. It's virtually immune to any interference from the surrounding environment.
So it's a super pure signal.
Extremely pure. But honestly, the most important thing about LNNPs isn't just the purity, it's the specific wavelength of light they naturally produce. It's in this zone researchers call the second near-infrared region.
Right, NIR2. Which is like the biological optical window.
Yeah, exactly.
Because, think about medical imaging. Visible light is famously terrible for seeing deep inside the body.
Yeah.
Like if you shine a really bright flashlight against your hand, you get that faint red glow.
Yeah, your skin just lights up red.
Right, but the light is almost instantly scattered and absorbed by, water and lipids and hemoglobin. You can't see anything useful.
And X-rays penetrate tissue, sure, but that's ionizing radiation. It damages cells if you use too much.
And ultrasound is safe, but it just doesn't give you that high-definition, molecular-level resolution that doctors really need.
Which is why NIR2 light is the holy grail here. It sits between about 1,000 and 1,700 nanometers. And at that specific wavelength, the scattering effect of human tissue just drops off a cliff.
It just slips right through all the biological noise.
Exactly. It's essentially a high-definition window straight into the body.
So the motivation makes total sense. If we could somehow turn these insulating nanoparticles into tiny controllable LEDs, we could literally light up internal organs or tumors from the inside out with perfect clarity.
But then, you hit that massive band gap wall. LNMPs are heavy insulators. Researchers have literally spent years trying to force electrical charge into them.
In failing, because trying to force raw current through the front door of an insulator just doesn't work. It rejects it.
Yeah.
So the Cambridge team, they didn't try to change the insulator itself. They built a translator.
A backdoor, basically.
Yeah. They coated the outside of these inorganic nanoparticles with this very specific organic dye. It's called 9-anthracene carboxylic acid, or 9-ACA for short.
Yeah, they essentially built a hybrid interface. By attaching those 9-ACA molecules right onto the surface of the nanoparticle, they completely change how the whole system reacts to electrical current.
I kind of look at the 9-ACA dye as like a molecular transformer. Because if you have a high voltage power line outside your house, you can't just plug your TV straight into it.
Oh, it would fry instantly.
Exactly. The raw currency is totally incompatible. You need a transformer on the pole to step down that energy and translate it into something your house can actually use. So these 9-ACA molecules act like molecular antennas.
That's a great way to put it. When you apply the voltage, the electrical charge doesn't even try to go into the nanoparticle. It goes straight into the organic antenna.
And the dye just happily accepts it. But catching the energy is only half the battle, right? The real magic is how it hands that energy over to the insulating core.
Right, the transfer. And this is where we have to dip into the quantum mechanics of it all, specifically this thing called the triplet state.
Okay, yeah, let's unpack that. Because electrons have this fundamental quantum property called spin, we usually visualize it as an arrow pointing either up or down.
Right. And in a stable molecule, electrons usually pair up. One points up, one points down. They cancel each other out.
Which creates a singlet state.
Exactly. But when that electrical charge hits the 9-ACA molecule, that whole stable setup gets violently disrupted. An electron absorbs the energy, gets kicked up to a higher energy level, and during that jump, its spin can actually flip.
So now you have two unpaired electrons with parallel spins, both pointing up, for example.
Yes. And that parallel alignment is what we call the triplet state.
And the crazy thing is, in normal optoelectronics, a triplet state is usually a dead end, isn't it? It's like a dark state.
Oh, totally. Quantum rules basically dictate that an electron in a triplet state can't just easily drop back down to the ground state and emit a photon. The spin would have to flip back at the exact same time, which is...
Forbidden transition.
Right, a forbidden transition in physics. So it can't release light easily. The energy is just trapped there. In most organic LEDs, triplet states are super annoying because that trapped energy just bleeds away as useless heat. It ruins your efficiency.
But the Cambridge team somehow turned that major flaw into the ultimate delivery mechanism. Because the triplet state is trapped, the energy doesn't just vanish instantly. It lingers.
Yeah, it has a long lifetime.
And since the 9-ACA molecule is physically bound to the surface of the lanthanide nanoparticle, that lingering energy actually has time to find a pathway across the boundary.
Through resonance. The energy gap of the triplet state in the dye aligns perfectly with the energy levels of the lanthanide ions waiting just underneath the surface of the insulator.
Like tuning forks.
Exactly like tuning forks. Through quantum resonance, the energy just jumps the gap.
Professor Akshay Rao from the Cavendish lab, I love his quote on this. He said they found a back door and that the organic molecules catch the charge carriers and basically whisper the energy into the nanoparticle.
A quantum whisper. I love that.
Right. It's not this brute force electrical shock trying to smash down the band gap. It's just this subtle quantum whisper.
And the efficiency of that whisper is what really blew the material science community away. The Nature paper showed that this energy transfer from the dark triplet state into the lanthanide ions, it happens with 98% efficiency.
Which is practically zero loss.
Yeah.
That's insane. They took raw electricity, translated it into a quantum state, and handed it across an impossible boundary.
Yeah.
And so the resulting devices, they're calling them LnLEDs. The performance metrics are kind of unbelievable for brand new technology.
Oh, yeah. They operate at a totally standard low voltage, about 5 volts. And this very first generation already hit a peak external quantum efficiency, or EQE, of greater than 0.6%.
Now, for someone watching who knows their commercial tech, 0.6% might sound a little low.
It does, sure, if you compare it to a modern display. But you have to look at the historical context. When the very first organic LEDs, OLEDs, were invented decades ago, they started with efficiencies right around there, sometimes even lower.
And now OLEDs run the entire global display market, every phone, every TV.
Exactly. Hitting 0.6% on your very first try, using a totally novel physical mechanism that shouldn't even exist, that is a massive validation. It proves the architecture actually works. Now the engineers can step in and start scaling it up.
Yeah, that makes sense. But I want to pivot to another spec they highlighted in the paper. They mentioned these LnLEDs have an extremely narrow spectral width compared to things like quantum dots. For the everyday viewer watching this, why does a narrow spectral width actually matter? Like, isn't light just light?
Not at all. Think of a broad spectral width like using a massive floodlight. You get this huge wash of photons covering all these different frequencies at once. But a narrow spectral width is more like a highly calibrated laser pointer.
Oh, okay. So it's way more focused.
Exactly. If you're trying to transmit data or, target a specific chemical marker in a test, you absolutely do not want your signal bleeding into other frequencies. That just creates noise.
And Dr. Zhongjing Yu, who is one of the lead authors, pointed out that that bleeding effect is why standard materials struggle so much with biomedical sensing. You usually need these heavy, expensive optical filters just to clean up the signal.
But because of that shielded nature of the lanthanides we talked about earlier, these LnLEDs natively produce that hyper-pure, isolated wavelength. No external filters needed.
Which means you can shrink the whole device down drastically. Since we can isolate that pure light natively and power it with standard 5-volt currents using these organic antennas, it changes everything about where these devices can physically go.
Oh, the miniaturization potential is the most exciting part. We're talking about a future of literally injectable or wearable optical beacons.
Injectable LEDs. Just let that sink in for a second. Imagine going in for a diagnostic procedure and the doctor injects you with a fluid that just has thousands of microscopic LnLEDs in it.
Just circulating right through your vascular system.
Yeah. And because doctors can now electrically control them and trigger that specific NIR2 light from the outside, they could map out the precise blood vessels of a tumor deep inside an organ.
In real time.
In real time. Like, surgeons could physically see the exact boundaries of cancerous tissue glowing through all the biological noise while you're literally on the operating table.
And we can actually take that a step further into treatment, not just diagnosis. Have you looked into photodynamic therapy?
A little bit. That's where they use light to activate drugs.
Exactly. Patients are given these specific drugs that remain completely inert, totally harmless, until they get hit by a very specific wavelength of light. The huge bottleneck has always been figuring out how to get that light deep enough into the body without just cutting the person open.
Oh, wow. But if the light source is already inside the body, circulating right alongside the drug.
You get perfect pinpoint activation. You could wirelessly trigger those tiny LnLEDs only when they reach the target organ. They emit the exact narrow wavelength needed, the drug wakes up, and it destroys the diseased tissue.
Without doing any collateral damage to the healthy cells around it.
Exactly. It fundamentally shifts our whole approach away from systemic treatments like chemo that ravages the whole body toward hyper-localized interventions.
That is just incredible. But it's not just medicine, right? Let's talk about the internet. Because global telecommunications rely almost entirely on firing pulses of light down thousands of miles of fiber optic cables.
Right, optical communication. And the huge limiting factor there is something called chromatic dispersion.
Which happens when you use light with a broad spectral width, right?
Yeah. The different wavelengths inside that light pulse actually travel through the glass fiber at slightly different speeds.
Yeah.
So over long distances, the signal physically spreads out and smears together.
Which basically caps how much data you can actually send. But since an LnLED has such a narrow spectral width that dispersion is minimized, the pulses stay razor sharp.
Which means we can pack those pulses way closer together. And it massively improves wavelength division multiplexing.
That's where they send multiple signals down the same fiber at once, using slightly different colors of light, right?
Exactly. And the purer your light is, the more channels you can safely cram into a single cable without them interfering with each other. These LnLEDs could legitimately be the foundational light source for the next massive jump in global internet bandwidth.
And the purity of that light is huge for sensors, too, like environmental or industrial sensors. If you have a light source that is perfectly calibrated to a single frequency, it's basically a flawless measuring stick.
Oh, absolutely. You could build advanced optical sensors to detect, trace chemical leaks in a massive manufacturing plant.
Or specific biological markers in a city's water supply, just by measuring exactly how that pure light interacts with the molecules as it passes through.
Dr. Yunsu Deng, another key researcher on this team, summed it up perfectly. He said the Cambridge team didn't just invent a better light bulb. They actually unlocked an entirely new class of materials for optoelectronics.
Because the underlying physics using an organic molecular antenna to dump triplet state energy into an insulator that's universally applicable, it's a completely new paradigm. We aren't just limited to 9-ACA and lanthanides anymore.
Not at all. Scientists basically have this massive unexplored playground now. They can start mixing and matching thousands of different organic dyes with all sorts of insulating nanomaterials.
Just building wholly bespoke devices for applications we don't even have the vocabulary for yet.
Yeah.
Because for decades, the tech industry just treated annihilators as, like, passive packaging.
Right, just the inert plastic or ceramic casing to keep the real electronics from shorting out.
Exactly. The active device was always the conductor. But now, the insulator is the engine.
The rigid boundaries defining what materials we can use for active computation and sensing, they're just permanently dissolved.
Which, leaves us with a genuinely provocative thought to consider.
Huh.
If we can now take a known, totally rigid electrical insulator and power it up just by slapping a molecular translator on its surface, what else is sitting in the dark?
Oh man, there are thousands of materials sitting on laboratory shelves right now.
Exactly. Labeled as unpowerable or entirely useless for active electronics. How many of those discarded, forgotten materials possess these incredible untapped properties? And they're just waiting for the right molecular antenna to wake them up and trigger the next tech revolution.
It definitely demands a complete reevaluation of our material archives. I mean, the definition of what's impossible in electronics just got much, much smaller.
And keeping you at the very edge of those expanding boundaries is exactly why we do this series. So to everyone watching on the Integratekh channel, thank you so much for joining us for this deep dive.
Yeah, thanks for hanging out with us.
If this breakdown helped you grasp the immense potential of this new optoelectronic paradigm, please hit that subscribe button. We are building a community dedicated to understanding the tech that is actively shaping our future.
And the conversation really doesn't have to stop here.
Yeah, exactly. Give this video a like and head down to the comments right now. We genuinely want to hear your perspective. Like, what do you think about the idea of injectable microscopic LEDs patrolling your bloodstream?
Does the medical potential excite you, or is the concept a little too science fiction?
Let us know. Share your thoughts below and stay tuned to Integratekh for more clear, engaging breakdowns of the most important new findings in the tech world. Until next time, keep questioning those impossible rules. Catch you on the next deep dive.